Okay, so last time at the second half of the lecture, we talked about the sort of conversion of our primary energy all the way to the sort of end use and services that they provide, right? And so who remembers what is primary energy?
Natural resources that you can mine, extract.
Yeah, exactly. So these are resources that are available in nature, and then we take those resources and do stuff with them. And so this class begins kind of a set of lectures on essentially the what we do with them at that sort of starting phase. Okay. Does anyone know what this map is showing? Yes. Yeah, that's right. So these are all of the power plants in the US. Okay. And so the dots represent a particular location of a power plant. The color of the dot represents the fuel type. And then the size of the dot tells us the generating capacity of any particular power plant. So you'll notice there's some trends here. Yellow is solar. You have a lot more of that on the West Coast and sunnier areas, and then starting to build out some on the East Coast as well. And then in the middle, there's like a big swath of wind. This is kind of where the best wind resources are in the country. And then we're mainly going to be starting with talking about fossil fuel plants today. And so the main ones are going to be the coal plants in gray and natural gas plants in orange. And those should represent, as maybe you can see in the map, kind of the largest circles and represent a lot of the generating capacity of electricity in the US. So you can see those kind of scattered throughout. And one thing you'll notice in California, there are no gray dots because we actually are not allowed to operate coal plants in the state of California. Yes.
With oil?
So oil is a thing, but and we'll talk about it kind of briefly. It is not a major generator of electricity because the cost to produce electricity from an oil plant is actually relatively high. But they do use them for what we call peaker plants, which is, so I'm not going to say like an emergency, but like in times where there's like much higher demand, you might deploy like oil plants. Any other questions about any of this? Yeah.
Is there one gray dot for coal in California?
Yeah, okay, so that one, there is a legacy coal plant. It doesn't actually produce electricity allowable into our statewide grid, but does technically use it, I think, for industrial purposes. But because it generates a small amount of electricity for local use, I think that's why it's still included in there. Yeah. And if you're astute, you'll also notice that there is one purple, yeah. Does anyone know where that is? Anyone know what plant?
Diablo Canyon.
Yeah, Diablo Canyon. That's the last remaining nuclear plant in California. Was originally scheduled to be decommissioned this year, but actually had its lifetime extended with approval from the legislature several years ago. And so it continues to operate, and we'll talk about nuclear plants next week. Yes, actually, that's a good reminder. So actually, no recorded lectures. Aaron Rabinowitz, who helped teach this course last year, he's going to do guest lecture on Monday and Wednesday. And so No recorded lectures. You guys still have to come to class next week. Sorry. Okay, so let's talk about extraction. And so we're talking about fossil fuel technologies today. So we're going to kick off thinking about fossil fuels and what are fossil fuels. So yes, it's basically dead dinosaurs. So these are fuels formed from decomposition of dead organisms and exposure to heat and pressure from the Earth's crust. Because it's organic material, right, it contains high percentages of carbon, and under heat and pressure, you form these sort of large carbon chains, okay? And fossil fuels basically we can think of as existing in three different forms of these sort of carbon compounds, right? So you've got liquids, solids, and gases. Okay, so liquids are essentially crude oil, right, of which we can refine and derive petroleum products out of. So we will talk about that more next week when we talk about some of the transportation pathways for a lot of the energy use. But today we're mainly going to be talking about the gas and solid forms, which we use more primarily. We use more primarily for electricity generation and sort of non-mobile electricity generation sources. Yeah, and so coal and natural gas. So natural gas, that's a kind of simpler molecule that we'll talk about, but coal is a much more sort of complex, and I can show that here. The left is an example of maybe a kind of molecular structure of the solid that represents what coal is. But it's not like one static chemical structure, right? It's basically this big jumble of hydrocarbons. And there are actually different grades of coal, and so we call these lignite, bituminous, and anthracite, and that is related to kind of the chemical composition and density, energy density of the coal. And so the way that I kind of try and remember this, so lignite is the lowest quality coal. It has the lowest energy density, and so we say L for low grade. And then bituminous is kind of the middle one, B for B grade, and anthracite, A for A grade. Okay. And so just one of the things to see in the coal molecule is that in addition to kind of just carbons, you also may have presence of other things like sulfur in here. And actually, it's also commonly contains other sort of heavy metals. And that has implications for when you combust it, which we'll talk about later. On the sort of flip side of things, natural gas is probably the simplest, right? So it's just methane, CH4, but that in itself, when you extract it, will also include impurities. And so things like carbon dioxide, hydrogen sulfide, oil, nitrogen, all this other stuff. And so even though the molecule itself of natural gas is fairly simple, there are processes that need to happen in order to reduce the impurities to some extent. Okay. So energy content, as I was mentioning, for your different grades of coal, you can see the sort of megajoules per kilogram. And so if you guys recall back to the class on Monday, we talked about those examples of energy density, and we were saying roughly 30 for coal. Well, that would be more representative of like bituminous and anthracite, but lignite, as you can see, can be, you know, half as energy dense as some of the sort of higher quality higher grade coals. Does anyone know where the highest grade coals come from in the world? Yeah, right here in the US. So we're kind of like the Saudi Arabia of coal. And so a lot of the, so Pennsylvania has some, but as far as I recall, I think the best places for coal in the US are more like Wyoming, Idaho, Montana area. There's a lot of good coal there. Okay, and so that gives you a sense of kind of the relative range of energy densities. For natural gas, we had actually mentioned this, right, when we were talking about BTUs, so about 1,000 BTUs per cubic feet. That can range depending on sort of the conditions and purity of your natural gas. Okay, and as far as reserves go, just to give kind of a sense, so this is stuff that exists out there in nature that we consider to be kind of economical to extract. And so actually the reserves number may change depending on like extraction technology and resource discovery. But so generally we're saying something on the order of about 1 trillion tons of coal, 33,000 exajoules, and so and then natural gas is quite a bit smaller in terms of energy content, so 200 trillion cubic meters at about 7,600 exajoules. And so to give kind of context for how much energy that is, right? Worldwide annual primary energy consumption is about 500 exajoules. So if all of our primary energy consumption were to come straight from coal and natural gas, if we had about 50 or 40,000 exajoules, how many years could we have at our current pace?
8,000.
Yeah, so quite a long time. This is this is not me advocating for us to use coal or natural gas. That's just the math. Okay, and just to give some sense of scale of that, right? And so visually, you've got oil, gas, and coal as fossil fuels in comparison to our sort of global energy consumption. Uranium that you would use for nuclear, and then the total amount of annual solar energy. So the top four, uranium, coal, gas, oil, is the total amount that exists that could be recoverable. But this bottom solar energy is just what you get in solar flux every year. So it's not this is not a like resource limitation in the same way. Right? Not saying that we could use all of that, obviously, but just to give a sense of scale. Okay, any questions about this? So moving on, talking about coal mining, there are a bunch of different ways and techniques that we essentially use to mine for coal. And so this gives kind of a high-level overview of types of sort of techniques and what these sort of mining's uses are called, right? So shaft mine, slope mine, drift mine, and these are used in different ways depending on the way that the resource itself is available within the land. And so you may have to employ sort of different techniques depending on the way that the coal might be structured, the coal beds are structured. A lot of them can be fairly environmentally damaging. A very common form of extraction is called strip mining, where you essentially remove the land in order to get access to the coal, and that has obviously pretty serious environmental consequences. So that's for coal. So for natural gas, on the left-hand side, you have a form of extraction known as conventional gas extraction, where you essentially kind of drill down into a pocket of natural gas and extract it sort of directly. Okay. In the early mid 2000s, a new technique for gas extraction was invented by an engineer in Texas. Does anyone know what that is called?
Fracking?
Yeah, fracking, also known as unconventional gas extraction. And so we're going to talk a lot more about fracking in a moment, but that has led to a pretty big transformation in the way that we use fossil fuels over the last like 2-ish decades, 1.5 to 2 decades. Yeah, I don't think I have this pie chart, but so does anyone know what sector emits the most greenhouse gases in the U.S. today? Yeah, I heard it. So transportation. But that used to not be the case. It used to be electricity was the largest emitting sector. And that changed because of shale extraction. It changed the economics of natural gas to essentially become cheaper than coal. And so there was a very big sort of flip-flop where we used to say we used to use about 40% coal, 20% natural gas in our electricity generation, and now it's more like 40% natural gas, maybe even more, and 20% coal, right? And so the numbers kind of flip-flopped. And that actually has led to the largest carbon savings in kind of the modern era, because natural gas is about half as dirty as coal. And so shale fracking, so from an environmental perspective, it's not great in the sense of like the local harms that happen from fracking. And also there are sort of arguments about the issues of sort of decelerating our transition away from fossil fuels. I think that's a very sort of legitimate argument. But the kind of silver lining, right, is that really more than almost anything else that has been done in our recent energy economy, this has decreased the U.S. emissions a lot more than anything else that has happened. Okay. Yes.
Do you think that we would have continued going after coal, or would renewables have maybe a chance for if there were any?
Yeah, so it may be the case that renewable growth would have been accelerated had this not happened. Hard to say. But even if that were the case, I would say the greenhouse gas implications would almost certainly still be higher, right? The amount of renewables uptake would not have been able to replicate the greenhouse gas reductions that happened as a result of fracking, right? For better or worse. And the other sort of piece of this is that, so okay, well let me describe what fracking is, right? So instead of going straight down into the resource, essentially you kind of go down and then you drill horizontally across, and so there are like fissures in the ground that may contain hydrocarbons, and essentially you inject water and other solvents that help dissolve some of this stuff. The hydrocarbons will saturate into the solution, and then you can extract it. And that is a procedure that lets you kind of explore sort of much larger shale regions and extract the resources in ways that were very much inaccessible in the past. And so it opened up a lot of potential resources. And so it just so happens that actually the US is a very rich shale, or is a shale rich country. And there are many sort of deposits, or they call them shale plays, that you can extract natural gas from. And that's one of the reasons why one of the results of the fracking innovation was the sort of driving down of gas prices by quite a bit. Yeah, so from the economics perspective, you can see sort of natural gas prices kind of substantially falling in the era following the innovation of shale. Okay, and then as far as processing, so this is all the steps that kind of happen post-extraction. For coal, it's not much. There's a little bit of this like filtration stuff that happens, and then they do some kind of processes, often at the coal plants themselves, to make them more amenable for combustion. And so that includes things like grinding and other filtering processes. Natural gas, on the other hand, right, from these wells, you have to do a lot of processing in order to get it to a stage where you have sort of a more pure stream of natural gas, right? And so you get these fluids that contain a lot of the dissolved hydrocarbons, and you separate everything out. So you have water, and it's pretty dirty water, right? And you have oil and gas. And the gas will go to processing, you compress it, and then send it out to whatever end use, right? And so that could be a power plant, but also we use natural gas for all sorts of things as well, right? To heat our water, to cook with, and so there is a whole sort of distribution system for natural gas that helps deliver that fuel to end use. Okay. Any questions about any of that extraction process? Yeah.
The deodorant that's added in the natural gas to make it noticeable if it's leaking, like in household, or what's the?
Yes. Yeah. So natural gas itself is odorless, but they add. I used to know this, like a dimethyl ether thing. Don't quote me on that, but it is a very odorous molecule that helps you, detect it by smell. So if there's like a leak or something, it's easy to detect. I don't actually know at what stage. Oh, there you go, right there. Yes, after it gets compressed, they add the odorant in. any other questions? Okay. So conversion. So, coal and natural gas themselves are not things that we actually use directly to provide services. And so we need to convert that fuel into a more sort of usable form. And so the big one, obviously, is electricity. So how do we generate electricity? It's not a physics class, so we're not going to get into the sort of math of this. But what I will say is the vast, vast, vast majority of all electricity produced in the country and actually in worldwide basically comes from spinning a wire through a magnet. Okay, so if you can make something move in a circle, you can generate electricity. And that basically describes a generator. So you've got two components, a rotor and a stator. Hopefully those names kind of help you remember the pieces, right? The rotor is the rotating part and the stator is the stationary part. So the rotor and the stator don't have to be specifically tied to the wire and the magnet. You could have the magnet moving, or you could have the wire moving, but one part has to be in motion while the other part is stationary. And so the magnets, there's a magnetic field, and if you move the coil through the magnetic field, then it will essentially cause electrons in the wire to move, and that is what electricity is. Okay? So, the way that we take advantage, or the way that we actually generate movement is through some sorts of heat engines. And so this is a way that we convert thermal energy into kinetic energy, right? And so we start with our chemical fuel, and then we translate that into thermal energy by combustion. And so heat engines are a way of taking the heat and translating that into kinetic energy. When whatever thing that you're working with is heated, that's going to increase pressure, right? And so this is ideal gas law. And this describes a direct relationship between temperature, pressure, and volume. And so when something is heated, pressure and volume have to increase, and when something is cooled, pressure and volume have to decrease. So where do we get the heat from, right? So this is fossil fuel combustion. So the equation, I'm sure you guys have seen forms of this before, right, in chemistry. So this is any sort of generic hydrocarbon. When we introduce oxygen and heat, right, it makes this is the literal definition of combustion, where you generate byproducts of carbon dioxide and water. This is a highly exothermic reaction, and so this generates heat. So natural gas combustion, for example, if we plug in the chemical formula, is very straightforward. There's one carbon, four hydrogens, two molecules of oxygen, lets you create carbon dioxide and water. Okay, and so technically speaking, if you could have a pure stream of methane, then the only byproducts you would really get if you had just methane and oxygen would be CO2 and water. But the way that we, where do we get the oxygen from? From the air, right? And so is our air only oxygen? No, right? So it contains other things. And so actually the most common molecule in air is nitrogen. Yes. All right. So In the presence of high heat, you could be forming impurities from nitrogen combining with oxygen. So that's nitrogen oxides. In incomplete combustion processes, you generate things like carbon monoxide. Incomplete combustion might happen where some of the methane ends up getting released and remains uncombusted, so you could have methane as a byproduct, and so a number of all these other things, right? So that has implications for air pollution that we'll talk about later. Coal combustion is like the complete opposite, right, of being straightforward. So if you recall that crazy coal molecule, where is it? Yeah, this guy over here, right? You're combusting something that is a lot more complicated in structure and may have a lot more impurities, right? So you can see the S's that represent like sulfur compounds within the coal molecule. And so in addition to all of the stuff that you might get from natural gas combustion, there's all of this other stuff too. So fly ash, bottom ash, boiler slag, and a bunch of gases. And then also if there are heavy metals in the coal, of which it's pretty unavoidable, you can get these byproducts of like mercury, arsenic, and heavy metals, and whatever those may react with within some of these combustion processes as well. So yeah, fossil fuel combustion can be can get pretty complicated in reality and lead to a lot of these impurities getting released as a result of the combustion as well. Yes.
Did they ever try to combine, like burning, say, a part coal and part natural gas to try and like offset some of these direct?
Well, so combining them, I don't think would really help with this particular problem. And from a like logistic standpoint, it's not something that's really done just because the process of burning coal and the process of burning natural gas, as we'll see in just a second, are like quite different in the way that it's actually done. In a coal plant, here I'll just jump over to here. The coal is combusted in a furnace, whereas for natural gas, we inject it directly into the turbine. And you couldn't do that for coal. That would be a crazy feat of engineering to do something like that, because you want to keep the stuff in the turbine pretty clean. Yeah. Okay, so I skipped around a little bit, but so how do we actually translate that thermal heat? What is the actual heat engine that I was referring to that lets us capture sort of motion? So these are turbines, right? And so this is the way that I change from thermal energy into kinetic or mechanical energy. So I extract energy from fluid flow and convert it into work. And so almost all electricity on Earth is produced from turbines. Doesn't matter if you're talking about coal, natural gas, wind, nuclear, hydro, they all go through turbines, except solar. Solar doesn't do this. Well, actually, even so there are forms of solar that do this. CSP, we'll talk about it a little bit later, but even solar can use turbines. Yeah, we won't get too much into the specifics about how the turbine captures it. There's a couple of different common turbine schematics, essentially, that allow us to take fluid flow and convert into work. A modern steam turbine, this is a picture of this. So you have lots of these incremental turbine blades, and essentially what that does is allow you to increase or decrease pressure from your fluid flow. And having multiple stages of that can increase pressure and then decrease pressure on sort of each side. So a steam turbine operates by taking high pressure steam flowing through the turbine and causing it to spin, which will then power your generator, which is the thing that actually moves the coil or the magnet. And steam works through a thermodynamic cycle known as a Rankine cycle. So a thermodynamic cycle is a cycle in which you are taking some kind of input, going through a different phases of thermodynamic states, and importantly, for it to be a cycle, it has to be able to return back to its original state. So that's kind of the key thing here. And so in this particular case, you have water going in to a boiler. That boiler introduces heat and changes the water into high pressure steam. The steam passes through a turbine to extract work, and the energy is translated right into this mechanical energy. And then you have a condenser that takes the steam back into water, right? And we need that stage in order to return back to the pump at the beginning, so that you can go again. Because the pump cannot, you can't pump steam in that kind of same way. Okay, any questions about this? So if you were able to get the maximum theoretical energy out of this whole process, you could, in theory, extract about 2/3 of the energy that's coming in. But the actual maximum efficiency for a modern coal plant is more something like 40%. And that would be actually pretty high. Most coal plants are going to be more in the 30%, low 30s to mid 30% in terms of efficiency. And when I refer to efficiency, I'm talking about extracting the energy content of the coal and turning it into energy in electricity. Okay. So a coal power plant leverages the Rankine cycle in order to generate electricity. So you have coal that gets introduced into a mill, it gets ground down into a fine powder. And does anyone know why we would do that instead of just throwing lumps of coal into the furnace? Increase surface area, that's right. So that will enable the combustion to happen faster and more efficiently and more completely. Okay, so what are we looking at here? We have combustion in the furnace. That is going to heat up a loop here that contains water, changes it into steam, goes through turbine. Turbine sort of moves the rotor in your generator, right, to generate electricity. And here we'll notice something kind of interesting. So this system here is a closed loop of water that moves through the turbine, and it gets cooled in a condenser here, which takes a different water source in a different loop to cool that water. And so why might we have this system as opposed to an open system with one single loop?
Cover the water.
To do what with the water?
Well, you're recovering the water and you're having two systems so that you don't have to mix the two, I guess. And
Well, so one thing that you'll see, if I were to go back to my my map of all the power plants, is that basically every coal plant is going to be located next to a body of water, usually a river, right? And so this river is actually the thing that provides, or that reservoir is the thing that provides the water that is used to cool the inner loop. So why don't we just send that water through the turbine? Yeah, exactly. So the maintenance issues that would arise from impure water and sending that stuff through the turbine would be a lot less efficient for the power plant because you'd have to shut down all the time and be cleaning your turbine. So you have a separate loop that's cooling a pure stream of water that actually gets passed through the turbine. And this water is the stuff that will heat up, and then out of the cooling towers you'll see like these big plumes of steam sort of coming out. But actually you'll see that there's two stacks here, cooling towers, which are much lower to the ground. You could go up to these things, and from a air quality perspective, would be totally fine because the only thing coming out of here is evaporated water. You don't want to be next to the chimney stack, which is actually much taller for regulatory reasons. They contain a lot of technologies to help clean the byproducts of combustion. But the tall towers are the ones that are spewing out the combustion byproducts. Okay, and so if you see pictures of these kind of coal plants, you'll see both cooling towers and these larger sort of chimney stacks. And the other reason why they're really tall is when pollution gets emitted, it disperses, right, and diffuses, and so technically by the time it reaches ground level, it has to be at certain concentrations, and so you have to keep it high enough that once it reaches ground level, that it's at that like regulatory required concentration. Okay. Questions about coal plants? Yeah.
I had a question about like the turbine you showed earlier.
Yeah.
Is there a reason why it's so like massive and metal? It just seems like in my head if it was like a lighter material, it would be easier to spin it and you get like a more rapid spinning generator, like a wind plant, you know, it's like the blades are carbon.
Yeah. So I think these are actually they're really well engineered, right? I believe it's not just pure steel. I think there's lighter forms or lighter alloys. One of the things that you have to balance against, right? So that is one consideration, but also, you know, you're dealing with high pressures and you're dealing with high temperatures, and so your turbine also needs to be built well enough to last under those kind of conditions. And so there is some kind of like optimization that happens to try and do things like making it light enough to operate efficiently, but making it strong enough to withstand whatever conditions that you're kind of like putting through it. Yeah. Okay. So some terminology as we think about efficiency is specific to power plants is something we call a heat rate. So this is a description of how efficient a power plant is. We typically talk about fuels, right, if you remember, in terms of MMBTUs for energy content, but we talk about electricity in kilowatt hours, megawatt hours in terms of energy content. And so a heat rate is exactly a description of the MMBTUs or the BTUs per watt hour, kilowatt hour, right? And so this is what we put in, and this is what we get out, right? And so if we were to translate both of these into joules, this number would always be less than what? Right, yeah. Oh, sorry, wait a minute. That would be output over input. It would always be larger than 1, because you're always going to get less out of your system because of efficiency losses. And so heat rate, it's kind of like an MPG, right? We're used to talking about miles per gallon for cars, and we kind of know what that means, but for a heat rate, there's like a different range of numbers, and we think about that to describe the sort of efficiency of power plants. And so this is kind of a range of different heat rates, right? And so for a heat rate, is it better or worse to be larger?
It's worse to be larger.
Sorry?
It's worse to be large if you want a lower heat rate.
Yeah. So you want less BTUs to generate more kilowatt hours. Yeah.
Is it an American thing to do BTU divided by kilowatt hours, or is it like globally that people express it like this?
I'm pretty sure it's global. Yeah. Yeah, even the yes, BTUs is metric and KWH is, or sorry, BTUs is imperial and KWH is metric. So it's yeah, it's a little weird, I guess. I'm pretty sure heat rates are universal, but maybe I'm wrong. Maybe if you can look up what some European papers and tell me if it's the same. Yeah, and so you could translate this into an efficiency number, right, by taking the inverse, and then the 3412 is the relationship between BTUs and KWH.
Sorry.
Yep.
Where does the 3.3412 come from?
That would describe the relationship between BTUs and kilowatt hours. So I'm going to get this wrong. So heat rate, it's 3,412 BTUs per kilowatt hour. I'm pretty sure. Yeah. Yes. Yeah.
It seems like the metric way of measuring is megajoules over kilowatt hour.
Ah, for Europeans. Okay, so it is different.
Not for units.
Yes. Yeah. In America, we use freedom units. Yes, we use BTUs. But it'll be, similar to MPG, where we think of them kind of relative to each other. That's kind of what you're thinking about here. And so whether you're using megajoules or BTUs, it's all about in relation to whether one power plant heat rate is higher or lower than another, right? You just don't want to cross-compare them, otherwise it wouldn't make any sense. That would be like doing MPG compared to, kilometers per liter. Yeah. You couldn't directly compare them.
Sorry. What
Yeah.
are the different step sizes on the
This shows kind of a distribution of the ranges of heat rates that you would see from different power generation facilities. And so these two are coal, and they're relatively higher. And then these three are natural gas, and then this one is oil. Yeah. So natural gas is actually going to be substantially more efficient than coal, but it doesn't look like it here. but I will explain why in a couple minutes. Okay. The other terminology to keep in mind is capacity and capacity factors, which tells us how much and how often do plants run. So when we talk about capacity, this is the maximum continuous power output of a power plant. And we are usually talking about power plants in terms of megawatts. That's generally the scale of power plants. You're usually in the hundreds of megawatts for decent sized power plants. Really large ones get into the thousands, and really small ones might be in the tens. Yeah, and so you can see that kind of here. Capacity factor, not to be confused with capacity, is the measure of the use of a power plant over time. And so this is the energy generated over any particular period divided by its total capacity times hours in a period. So if you have a capacity factor of 1, that means you're on all the time. If you have a capacity factor of 0.9, that means you are on for like 90% of whatever time period we're talking about. Usually we think about capacity factors over like the course of a year. And so I might say something like a nuclear power plant is almost always on. The only times it's down is for like operations and maintenance typically. Compare that to a modern day gas plant, which might have a capacity factor of 60%, which means it's running 60% of the year, coal 50%. And then just to give you guys a sense, right, for renewables, right, the sun doesn't always shine, the wind doesn't always blow, and so capacity factors are a way to describe how often you are able to use the resources. And so even if you have a 1 gigawatt nuclear plant compared to a 1 gigawatt solar farm, the capacity of those two power generation facilities is the same, but the actual amount of energy that they'll produce over the year is different because they're on less. Okay, and so wind, we're typically in the like mid-30s% on average, and solar is about 20 to 25% on average for capacity factor. Yeah.
I think I read once that it takes like up to 4 hours sometimes for these plants to start from
Yep.
the time they turn on, so till they can start producing energy from just heating up and stuff. So like, how do you take that into consideration? Is that like from the time they produce electricity or from the time they turn it on?
Yeah, well, so luckily this equation kind of takes care of that because, yeah, it's included in here because the amount that might be generated includes, so what you're describing is called ramping and startup and shut off time. And so maybe you're going up to 80% of your capacity, but it takes a couple hours for you to do so. So you're generating less electricity, and so we actually will say your capacity factor in those time periods is going to be lower. Yeah.
This is like average of nuclear.
Yep, exactly. Yeah, and so the ramping that you're talking about, so different power plants have different capabilities to sort of ramp up their turbines, and not only the turbines, but like this, for example. So a coal plant tends to actually have a slower ramp time, and that is because, well, it takes me time to like boil water, right, and send it through a turbine. Whereas natural gas, for example, and we'll see this in just a second, you literally just inject it into the turbine and blow it up, right? And that's actually much faster to ramp up. And then like a nuclear plant would be even slower because you have to start up the fission process and then heat up the water. And so different power plants will have different ramping times, and that does play a role in the like operation and the way that they're used, but the actual contribution of ramping to capacity factor would be pretty minimal, I would say. It's not often that you're like turning off and turning back on like in constantly, and so it is accounted for here, but it's not going to make a big difference.
Why is hydroelectric so low there?
Yeah, so hydro, hydro is kind of a unique case. We're going to talk more about this next week, but hydropower is not able to be on all the time because it uses like a reservoir of water resource, and so there's like a limitation to being able to, let's say in a particular season, you may have less water, and so you want to be turning it on at kind of strategic times, and so they don't full bore turn. It's pretty rare that a hydro facility would full bore be able to use the whole thing. And part of that is intentional, right? So I could size a hydro facility to be on all the time, but I could oversize it and then be able to use the sort of flexibility of getting more electricity at certain times, which the system deems kind of more valuable often, right? And so there is some trade-off there, and usually they tend to value that flexibility more than just having it on all the time. Yeah.
What is PV where it says typical residential
Yeah, that,
up in capacity?
yes, the residential PV is solar on your rooftop. So PV is photovoltaics, yeah.
And CCGT?
That's a combined cycle gas turbine, and so I'll talk about that in just a couple minutes. Okay, I do have a slide on ramping and startup. So how fast can plants change output? So that's the ramp rate. Also, there's if you turn off a plant, you can't just turn it back on instantly, and so there's another thing that we think about with startup time, which is the time that it takes to kind of sync up with the grid and have everything at kind of the optimal sort of operating like temperature and status. Yeah.
How is like climate change affecting like ramp-up times, right? 'Cause it's really hot day.
Oh no, that I would say not at all, because when we're talking about like the hot operation, that's like at much higher like these are like combustion level temperatures, right? And so ambient temperature. Ambient temperature typically is not really going to play that much of a role, unless I would say that the only exception is at freezing levels. Weird stuff can happen if you are if you don't have proper like insulation and barriers against cold, and that actually happened in Texas a number of years ago, and prevented some things from operating. So. But I would say generally speaking, ambient temperatures don't really make it that much of a difference here, yeah, with that exception. So you can see kind of the ramp rates that I was talking about, right? So nuclear, more than 12 hours, coal 1 to 3 hours, CCGT 30 to 90 minutes, and then just a single combustion gas turbine 5 to 15 minutes, and then the percent of the capacity that they can do per minute. Yes. So this is just kind of a reference slide. I'm not going to go through it, but it gives some idea of heat rates, capacities, capacity factors, ramping for coal plants. Okay. Let's take a 3-minute break because I'm moving a little bit slowly through the slides. I want to make sure we get through everything. Hey. All right, 3 minutes. So next up from coal plants, we're going to talk about natural gas and the way this operates. Okay, and so this is a gas turbine, which is going to be different from the steam turbine in a coal plant, where the steam is pressurized externally. Well, not totally externally, but the steam and all that heat is generated externally and then passed through the turbine. Whereas in natural gas plant, we use a gas turbine, which uses a different thermodynamic cycle known as a Brayton cycle. So there's 3 components to a gas turbine. So you've got your upstream gas compressor, and so you have air coming in over here. It gets compressed through these turbines, and so it's pressurized in the middle. At the end, we have a downstream turbine that's kind of operating on the same shaft, and that will take advantage of the sort of pressurized gas that's kind of moving in this direction. And then you have the combustion chamber in the middle, and this is where you have natural gas getting injected, mixing with the pressurized air and combusting, which is the thing that essentially spins the turbine, and you eject your extremely hot gases out of this nozzle at the end. Does this look like anything to you guys? Yeah, so if you've ever flown on a plane before, that's what this is. And in fact, you could rip one of these off of a plane, stick a generator on it, and you would have a natural gas plant. Like, quite literally, you could do that. But you couldn't do it in reverse for obvious reasons, I think. Yeah, so Brayton cycle, it takes advantage of this spinning turbine, and then we use that to power a generator. The efficiency of a Brayton cycle in practice is around sort of 47%, and you're usually getting efficiencies kind of in the low 40% for natural gas plants in operation. Okay. So gas, you'll often hear people saying that gas plants are far more efficient than coal plants, right? But it doesn't look like that in this particular case, right? When we're talking about the sort of energy content of the gas and getting that into the electricity in the Brayton cycle. But what's coming out of the turbine? Yeah, heat, a lot of heat. Okay, and so modern day natural gas facilities can actually take advantage of that. And so you have you do have facilities that are known as natural gas plants that just do the combustion part, but then you also have facilities that have something called combined cycle. And so in this case, you've got your gas turbine, which is doing all the stuff that I was just describing, but here it also has a steam turbine, a second turbine. And what's happening is it's taking those hot gases, and then it's using those hot gas byproducts to heat up water, turn it into steam, and send it through a steam turbine, a la the same sort of thing that we're talking about with coal, right? And so you've got a boiler, steam going through condenser, going back to the original part of the thermodynamic cycle. And so you've got two different thermodynamic cycles happening, right? Gas turbine combustion happening here, spinning a gas turbine generator and releasing exhaust gases. Those exhaust gases heat up a closed loop of water, where I generate steam, send it into a steam turbine, spin this one, and get electricity through a different steam generator. Okay. And so there, I'm able to take advantage of some of the heat that I would waste, and your efficiencies now can get even higher, right? We're talking about something on the order of 60% efficient as opposed to like 35 to 40% efficient. And so this is why people talk about the efficiency of natural gas plants versus coal as being much higher. Okay. So some of the operational attributes of gas plants. So the heat rates, 9,000 to 11,000 BTUs. So those are gonna look similar to coal, but when you do combined cycle, instead of the simple cycle, which is the single gas turbine, you're now more on the order of 6,000 to 7,000 BTUs per kilowatt hour. Okay. Simple cycle gas turbines tend to be a little bit smaller, and that's entirely just because once the scale economics are reaching certain sizes, you might as well do the combined cycle, and so most of the combined cycle is going to be larger in capacity, in addition to the fact that they're getting more sort of capacity due to the second turbine. And the economics are usually having to do with getting turned on at certain times where they can make more money, whereas combined cycle turbines want to be on a lot more often. It's more economical. The ramping rate and startup time of a simple gas turbine is much faster than combined cycle, right? Because I don't have to boil any water. I just turn on that first turbine. Okay. Oil generator, I'll just like really quickly talk about this. So this is basically the same schematic as coal plant, right? It uses a steam generator, and instead of combusting coal, you're combusting oil. And these tend to be, if we look at the operational attributes, the heat rates are actually kind of similar in terms of the energy content that you're able to extract out of it, but the fuel itself is more expensive, and so this tends to be used quite a lot less, right? So the capacity factor of oil plants is less than 5% in the US. And so we use this when the demand for electricity is really high. This is kind of like a last taker position, and so they'll turn on these plants only when they get paid a lot of money. Okay. This is a nice little plot that gives us a little bit of historical context into the sort of build out of generators in the US. Back in the 60s and 70s, or I should say 70s and 80s, is when we saw a sort of large growth in different types of power plants, including coal, natural gas, and nuclear. Whereas in the mid-2000s, right, remember when I was talking about shale and fracking and how that introduced the ability for our power system to go after a lot more natural gas. We have a huge amount of natural gas construction happening, and so there's a lot more generators of that fuel type today. And then in the sort of most sort of modern era, the sort of dominant capacity that's being built is renewables, right? So wind first in the like late 2000s, early 2010s, and then now solar, with the economics being what they are, being kind of more sort of dominant in the like built out capacity. And you can see the generation type evolution. And so up until the 2000s, dominated by coal, and then that starting to shrink as a result of natural gas becoming more sort of economical. questions? Okay, and now we'll talk about some of the economics of these things. So where do the costs of power plants come from? So there's different components of cost when we think about economics. So overnight capital cost. So this is a number that we talk about in terms of like a one-time build that excludes kind of the financing, which can kind of muddy the waters a little bit when we think about the economics of power plants. And so this is kind of what the cost would be if you kind of just build it overnight. Fuel costs. This is oftentimes the sort of dominant variable, and that's tied to the cost of the fuel in the market. You also have operations and maintenance costs, and we kind of divide this into two categories. You've got fixed costs and variable and O&M costs. So fixed might be like things like staffing, maintenance contracts, taxes, right? So whether or not your power plant is running, you got to pay the people who are operating. But then you also have variable O&M that have to do with consumables, and then things related to wear and tear, right? And so if you're running it a lot, you might have higher variable O&M because of like hardware degradation from use. And then there's all the like lifetime financing assumptions that might get tied into this. And don't worry about this too much. We're going to talk more about like some of the ways we think about this in a different lecture. Yeah, and so to give ranges of costs, what this kind of looks like. Yeah, so coal. So this is standardized to a unit of capacity, so per kilowatt. Coal these days might be quite a bit more expensive, which is why we're not sort of building as much of them anymore, coupled with the fact that, you know, so they had always been a little bit more expensive because of the size and scale, but the economics of the cost of the coal fuel itself was one of the things that allowed it to, or got people to build it despite sort of higher overnight costs. But that's not true anymore, right? Combined cycle, and then simple cycle natural gas over there. Oil, quite a bit more expensive than natural gas, and the fuel itself is going to be quite a bit more expensive as well. The last one, CCS. Who knows what CCS is?
Carbon capture.
Yeah, carbon capture and sequestration. So this is like clean coal. If you're able to take the greenhouse gases, specifically carbon dioxide, combustion byproducts, and you're able to sequester it, there's a variety of different ways that you can do it. I think the most common ones that people are talking about are through some chemical means. You can essentially reduce the greenhouse gas emissions of the coal plant, right? And that can be, you know, brought down to almost zero if you could actually do it correctly, but the economics of it make it very difficult as well. Fuel costs. So this is on a per MMBTU basis. So again, they're kind of standardized. But the MMBTUs is the energy content of the fuel, so it doesn't take into account the efficiency of using the fuel. And if you were to do that and you're doing it on the kilowatt hour end, that's kind of the more apples to apples comparison. And you can see the cost range here. And then oil is like an order of magnitude more expensive. questions? Yeah.
Do the coal plants differ in like their approach to limiting criteria pollutants from renewable fuels?
So they, yes and no, in the sense that if you are building a CCS plant, it's going to be like a newer plant, and so you have more modern controls and that sort of thing. But I wouldn't say that they're, for the criteria pollutants, that they're necessarily doing anything like different other than being newer and more state of the art.
Gotcha.
Yeah. Yeah.
Can you go back to the previous slide? I think?
Sure.
I'm just not sure about the like why is it so expensive per kilowatt? Does it mean that for every extra kilowatt so for power production it costs like in the thousands of dollars?
Yeah, but so be careful about the distinction between kilowatt and kilowatt hours, right? This is about size and capacity of what you can produce as opposed to an amount of energy that's produced, right? And so this is just saying if the size of the plant is of X size, it's going to cost based on this kind of scale, right? And so if I wanted to build, let's say, at $3,000 per kilowatt, a 1 gigawatt coal facility, right? So how much would that cost? That would cost $3,000 times 10 to the 6, right? So it would cost $3 billion to build a 1 gigawatt coal plant. Now, what can I get out of it? Every year, if I have it on the whole year, I could get a gigawatt hour, I get 8,760 gigawatt hours a year for 30 years, right? And so this is about a capacity number as opposed to an energy number. Okay, breaking down a little bit more operations and maintenance. So fixed O&M, costs that occur regardless of how much the plant operates. So labor and staffing is the majority. You have routine maintenance like inspections, replacement parts. Overhauls might be longer term things. And so like refurbishing a turbine. Taxes, and then environmental compliance might be a cost as well. So especially if you're a fossil fuel plant, you have to do what's known as continuous emissions monitoring, SEMS. That actually feeds into like an EPA database that's publicly available. It's actually a way that you can get a pretty good look at ways that plants across the U.S. operate. At least you could. I think that the current administration is doing some weird stuff with SEMS right now, but okay, operations and maintenance. There's the variable piece of it as well. So these are things that often scale with generation, and so these are costs that get incurred when you're actually running the plant. So consumables. So this is like consumables that don't include the actual fuel that you are combusting. So things like scrubbers for pollutant controls, chemicals for water treatment, waste handling and disposal. So we talked about like in a coal plant, you have buildup of like flue ash, fly ash, a lot of those solids and heavy metals. You got to figure out ways of cleaning and disposing that. Maintenance from wear and tear are just, these things are actually pretty impressive feats of engineering, right? You are subjecting turbines to extreme temperatures, extreme pressures, and so, like a car engine, you got to take care of it. You got to do maintenance on it. Auxiliary power. So this might be power for the actual facility that you're working in. water, and then regulatory and operating fees. Yeah, so this is like staffing for different types of power plants. So coal, you might have 60 to 100 full-time employees, whereas combined cycle you might have 20 to 30 for the same size. So the operations and maintenance fixed piece is going to be smaller for gas turbines. Coal plants, these are some cleaning of some of the systems that are in coal plants. This is a inspection of the heat recovery steam generator in a combined cycle gas turbine plant. And to give a sense of what these costs look like, something like this. So your fixed O&M is always going to be there, and then your variable O&M can be smaller or larger depending on how much you're actually producing, right? So note that the units are different here. This is in dollars per capacity size, and this is in dollars per energy or cents per energy generated. So don't compare this row directly with the top one. It's more about comparing across the columns. Okay, and so when we think about the economics of these things, there's like a lot to keep in mind, right? How do we actually compare the cost to build something that generates electricity for us? So luckily, there is a nice little catch-all that folks in the electricity sector and actually more broadly in energy think about as a way to do a more apples-to-apples comparison, which we call the levelized costs of electricity. And this is a way of not only taking all these terms that we just talked about in terms of the overnight costs, the fixed and variable O&M, the fuel costs, but it also thinks about how much the power plant actually gets used, right? Because the capacity factor of a nuclear plant is different from a coal plant, is different from a solar facility. So levelized costs is the way that we can put everything into the same kind of metric and compare cost to generate power. My equation got a little messed up for some reason. Okay, that's all right. So basically, you add up all of the costs that we just talked about, and so you have your fixed costs, and then you have all of your costs that are sort of annualized from your fuel use, your operations and maintenance, and then we do essentially like a net present value of all of that, and then divide it by the energy that's actually produced by that generator over its lifetime. And so that will give us a cost to generate an amount of electricity over the entire lifetime of that particular facility. I will clean this equation up and post it, so sorry about this mess here. Okay, and so the levelized cost of electricity or energy is important because this is a way that allows us to do these comparisons that have different lifetimes and fuel types and costs and utilizations. This is a way to screen for like cost effectiveness of different a sort of plethora of generation options. This is also a nice way to do analysis where you can look at all of these factors that shape the competitiveness and see why certain things might look more favorable in one versus the other. There are some limitations of an LCOE to think about, and so one, because you just divide by the total amount of energy produced, it doesn't care about when that electricity is produced, and that in itself has value, right? And we know that electricity is worth more at certain times and in certain places than others, and we are not able to kind of account for that directly in this metric. It also excludes system costs, and so some of this you might be able to roll into it, but oftentimes you're just looking at the generation. And so there is a difference between, right, building a natural gas facility like in the heart of LA where you can set up the transmission of electricity really close to the population centers that are using electricity. Whereas if I have, a wind farm out in, Wyoming, and I have to build out a really long transmission in order to get that electricity to people who are actually using them, right? And so that would not be included in, let's say, a traditional LCOE. And there are other sort of system costs that are similar to that you wouldn't capture directly in this metric. And yeah, so this is not really a market price type of thing. This is more just examining relative costs. But all of that having been said, it does let us do these comparisons here. And so this is an analysis that was done to look at LCOEs across different generation types. So the ones that we were talking about are down here in the bottom where we're talking about conventional resources, but you can also see how that stacks against renewable energy resources. So gas combined cycle has been kind of the gold standard for a long time, and you can see compared to conventional stuff, it's not as economical, or sorry, it is more economical than all the other conventional stuff. And so coal is more expensive, nuclear is a lot more expensive. Gas peakers, and so those are your single combustion turbines. These are still built, but for other sort of nuanced reasons than just purely trying to think about the LCOE. And one of the nice things is that over the years, right, in renewables, and we'll talk about this more in detail later, but renewable costs have come down where they are now kind of more directly competitive with your combined cycle gas turbines. And that's right, taking into account things like your capacity factor, but maybe not necessarily taking into account things like the transmission that might still be quite a bit higher than for gas. Okay, any questions about LCOE? So well, I'll say that we're kind of breezing through this piece of it, but we'll later have kind of a energy economics lecture where we'll go more into detail about the implications of like the financing and lifetime and how we do the LCOE calculation in more detail. So this is kind of like just a first peek at that, and then we'll get into how we actually do it later. Okay, nothing about LCOEs? Yeah. And this chart is also, a couple years old at this point, so it might be interesting to dig up a more modern one to see if things have changed at all. Okay, the last little section we're going to talk about for today is the environmental implications and emissions that are associated with fossil fuel plants. Okay, consequences. So power plants are the largest stationary sources of air pollutants globally and have been for a long time. And so we think about air pollution in kind of two different categories, right? And so there are impacts to climate, and so those are what we refer to as greenhouse gases, and then there are impacts to like local air quality, and so these are things that might affect human health directly, right? And so you've got GHGs and local air pollutants. And so the climate ones are things like carbon dioxide, methane, and 2O, and things that affect your respiratory health and other actually health is NOx, SOx or SO2, and particulate matter. We also think about these pollutants in categories of direct combustion byproducts, right? And so when you do the combustion, it releases these things and they travel through the air and affect either you or the climate in certain ways. And then there are combustion byproducts. And these are things, impurities or things that are not the direct combustion byproducts that we think of from oxidation, but as a result of impurities in the fuel air mixture or from incomplete combustion. So from fossil plants, the main things that we are really concerned about, so carbon dioxide, so this is your main pollutant byproduct, and that leads to climate change, right? And so hopefully you guys are all familiar with that. With NOx and SOx, these are combustion byproducts that happen. So NOx is a result of the combination of nitrogen in the air with oxygen and high temperatures. And then SO2, that's more going to be coming from coal than anything else. You're not going to get a lot of SO2 and SOx from natural gas combustion. It's mainly sulfur that's contained within the coal. There is some, but it's fairly negligible. And that can lead to the formation of particulate matter in the air, as well as acid rain. Particulate matter, this is probably the thing that influences respiratory health the most. We'll talk about that in more detail in a second. And then heavy metals. So what is particulate matter? So these are mixture of solid particles and liquid droplets in the air. We think of particulate matter in size categories, and so the common ones that people talk about with pollution are PM10 and PM2.5. So PM10 means you have particulate particles that are 10 micrometers or smaller, and PM2.5 is finer particulate matter that's 2.5 micrometers or less. So this is a little thing for scale here. PM90 in blue, that's like a grain of sand. PM50 in green, that is the thickness of a human hair. And then PM10 in yellow, that is dust, pollen, mold, looks something like this, so quite a bit smaller than the human hair. And then 2.5 are these little white dots, and that's basically from things like soot, very, very small, fine particles. So PM10 is not great to be ingesting all the time, but actually our respiratory system does a pretty good job at capturing a lot of those particles. And so your like snot and saliva prior to the airway will grab a lot of PM10 stuff. 2.5 is different. That stuff will go straight into your lungs. That will bypass a lot of the protections that you would normally have against PM10. And it is known to be a sort of major risk factor for mortality across the world. And yeah, people have done research and analysis showing that PM 2.5 leads to excess deaths in the order of millions of people every year. Typically speaking, right, the dirtier your combustion, the more PM 2.5 and PM 10 that you generate. What does that look like in the United States? So this is a decade ago, although probably hasn't changed hugely. Maybe background levels in some regions have decreased a little bit, but this is kind of the sort of distribution of PM 2.5 concentration. All of this is from combustion, okay? So a lot of what you see here in these populated, in this sort of eastern half of the country is from combustion from coal plants, 2.5. Here is from mainly transportation. This is a lot in the sort of LA metro region, and then getting kind of spread out through Central California as a result of the way that air kind of disperses in the state of California into the valley. Any questions? Yeah, and so it's some places have been a lot worse historically, and I'll also say that while these concentrations haven't changed much in maybe the last like 10, 15 years, back in the like late 70s and 80s, a lot of the pollution controls that were implemented by newly formed EPA did actually lead to a pretty big decrease in pollution kind of across the board. And so if you were to go back into the 50s, 60s, 70s, 80s, and you were to observe changes, it would be probably a little bit more substantial. Yeah, and so as I was mentioning, the carbon dioxide, right at the beginning I was saying the sort of climate impacts of fracking has changed quite a lot as a result of natural gas introduction, and this is kind of why you see that happening, right? So natural gas is essentially half as dirty as coal when it comes to CO2 as a greenhouse gas. Sulfur, SOx and SO2, as I was mentioning, that's mainly present in coal, whereas natural gas, you have essentially very, very little of that, not too big of an issue. NOx is going to show up anytime you're doing these high temperature combustion, so this continues to be kind of an issue. And then particulates, not as bad with natural gas, right? Because the fuel stream tends to be a lot cleaner. Whereas with coal, it's going to be quite a bit worse, but there are certain control technologies and scrubbers that will help reduce some of this stuff, but not totally to zero. So what are some of the emission control technologies? For particulates, we have these precipitators called ESPs that can remove fly ash from coal combustion. For NOx, you have certain catalysts that can help select for that in the air and reduce concentrations of NOx, and so that's one of the emissions control technologies that has helped bring down NOx levels. Heavy metals, so sorbent filters essentially are ways to get rid of this, and then for SO2. So kind of, you don't need to know specifics about these technologies, but in large part thanks to regulatory efforts by the Environmental Protection Agency over the years, a lot of these technologies have been introduced, right? These are all sort of externalities that normally a power plant operator or owner wouldn't need to like care about without the sort of presence of regulation. And so some of these things spun out of the Clean Air Act, right, in the 1970s, which is kind of the foundation for a lot of that emissions regulation. And there are a number of EPA programs that have been implemented to essentially reduce the environmental impacts of all of the combustion that we do. Yeah.
I'm just curious on the previous slide, like for the fly ash and some of the mercury metals.
Yep.
From what's recovered, if it's in filter, does it just like go to landfill, or what is the kind of like follow up kind of process?
Yeah.
after
So
scrubbing it?
yes. So it's like solid material, and then you can just dispose of it. I don't know if it actually goes to landfills. They might like. I think they like dig up a local site and just like dump it there, which okay is ostensibly also bad, but it's yeah. So there's a trade-off in terms of like health outcomes versus some of the like localized impacts, and yeah. So from like if I were to put on my economist hat, which is not like totally, you know, I'm not trying to be dismissive, but like the level of disparity and impact of like burying it versus like letting it go in the air is like so widely different, right? That yeah, I would say it's kind of like a third or fourth order problem compared to like a first order problem for that. Yeah.
I was just curious because like gypsum can be used for like other purposes.
Yeah, no, they don't recycle any of this stuff
Yeah.
really. Yeah, for it's too like toxic and yeah, hard to deal with. Yeah, and it's not economical to do stuff like that. Yeah. Yeah. So. Number of different programs and rules that have kind of shaped the industry, and at least for local health air pollution type things have really actually improved, you know, for a number of decades. Greenhouse gases. Maybe a little bit different, right? There are specific programs about reporting that are great and let us have an understanding of impacts. But as far as like cleaning it up, it has, I would say, less been on like EPA regulation and been more on sort of other transformational policies that are pushing us towards like clean energy. Yeah, so there is good progress, right? So this is the amount of electricity generation, and so in kind of lockstep with that for a long period of time, CO2 emissions were kind of one-to-one with that, but then, you know, starting to decrease, and that decrease is like, I would say the vast majority of this decrease is natural gas use as opposed to coal, but the like contribution of things like renewables is going to start making a bigger and bigger dent here as we kind of move out into the future. Yeah, so we'll close out. Key takeaways: everything relies on spinning a turbine and a generator. For operations, there are things to think about that are different about these generators. The economics piece of it plays a role into why we see things getting used. And then for environmental impacts, there are a number of things to think about, both from the greenhouse gas emissions perspective, and what that means relative to the fuel types that we use, but then that generally speaking, the trend has been good for local air pollution because of regulatory controls. Yep, so that's it for today, and I won't see you guys here next week, but still come because we will have our guest lecturer for next week. Not recorded lectures.
I saw that you're gonna post the homework next week.
Yes.
Comments about that?